Hello, class. I just want to start out by saying that I think that I have helped the Logitech, the horrible Logitech camera. Why would they buy those cameras? Who knows? But there's an artifact that comes with these about the autofocus, and I got on the web and I looked at a bunch of things, and people had come up with several different ideas. You had to basically turn the autofocus on by downloading other camera software that would allow you to turn that off. I have turned it off, and I think that I've done some experiments, and I think that the thing is off now. The auto, it's supposedly much better by turning that autofocus function, which doesn't work very well, especially for 12 to 18 inches away. What do you know? That's, I could, yep. But that's how life goes. And of course, the way that you are successful in moving through life is how you take the challenges that life throws at you and overcome them. Right? There's a lot of people that cannot overcome them, and that defines their life. As engineers, we have a lot more capabilities in mathematics really mathematics and just an understanding of physical phenomena that helps us become more capable to handle those challenges, just like this coronavirus challenge that's been thrown at us. All right, well, today what I want to do is I want to talk about right-handed coordinate systems. It's a process by, doing these, figuring out the autofocus and everything else. So, it seems to be working, like I say, much better now. Why do I say right-handed coordinate systems? And I think I've discussed this with you before, but let's just draw some coordinate systems here. There's my XYZ coordinate system. Why don't I say that this is X, this is Y, and this is Z? And I think everybody can see from there that if I take my right hand and I lay it along the x-axis, and then I curl my fingers toward the y-axis, the z-axis obviously is going to be out of the plane. It certainly wouldn't work if I did it with my left hand, would I? Because that's why it's called the right-hand coordinate system. The reason that we have right-handed coordinate systems is because we are right-handed. Mainly, everybody's right-handed. They've now started to figure out that actually left-handedness isn't just something that happens, it's a birth defect. And that may have something to do with the reason that left-handed people, unfortunately die 7 to 9 years younger than their right-handed counterparts. Now I want to look at this. Now we have looked at this before, so that if we had a differential surface areas, right? If I had a differential surface area where I held z constant, and I was just looking in the xy plane, that would give me dx dy, right? And then the second one would be, if I was looking at the yz plane, dy dz. And the third differential area, if I was looking at the xz plane, would be dx dz, right? So we know all of those. We also know that our differential volume is going to be dx times dy times dz. All of those very straightforward. Let's write down a couple other things for this. Now, what are the boundaries for all three of those axes? So I know that I can start at minus infinity, and minus infinity is less than x, and that's less than positive infinity. So the x-axis goes from negative infinity to positive infinity. The y-axis goes from negative infinity to positive infinity. The z-axis in the Cartesian coordinate system goes from negative infinity to positive infinity. I think everybody sees that, right? If I was to hold z constant, if I was to hold z constant and I was to let x and y be any value that they wanted to be, that would create a plane. Now, would it create a plane at z equals 0? No, I'm just holding z constant. But if I held z constant, let's say that I held z constant, but I let x and y change, then I would have a plane, right, at that point where z is, and that plane would extend over, you know, the whole thing. Same thing would be true if I held x constant or I held y constant. I would get a plane, right? So that's what I want to look at for the other coordinate systems that we have too. And of course, what we want to do is we want to design the coordinate system so that it fits with the geometry of the problem, right? So that's my coordinate system. I'm going to draw another, we're going to talk, that's my Cartesian coordinate system, obviously. I'll just write Cartesian, although I'm sure that everybody knows that it's a Cartesian coordinate system. And the next one that we're going to look at is going to be the cylindrical coordinate system. So the cylindrical coordinate system, and what I want to do is I want to overlay the cylindrical coordinate system on top of a Cartesian coordinate system. So let me just redraw the same thing that we have there. I'm going to put, you know, z and then x, but I'm going to do it in red so that you can see that. Oh, wait, what am I doing? Give me that. I've even got these backwards, don't I? Oh, I'm so used to, you know, drawing it the other way. But anyway, let's get back to this. So this is my x-axis, and this is my y-axis there, just like I've got over here. But what I want to do is I'm going to overlay. I'm just going to continue the negative z-axis there too, so that you can see how the cylindrical coordinate system works with that. Now, the cylindrical coordinate system, if I was to look at rho, right? Now, rho always, it lies in the xy plane. So let's look at a cylinder here that I've got. I'm just going to draw a cylinder, right? Just going to draw it down here so that we can just see how a cylinder, and why, of course, we call it cylindrical coordinate systems. Now, when I want to define a point on here, I would draw yeah, well, let me just do this. Let's say that I wanted to how can I there, you see how that goes? So I'm drawing that sort of in the XY plane, and this would be a radius in the XY plane. I mean, you can do the reading too. This would be a radius. And I just want to see what your book is calling it. Well, your book is actually calling it R, But I'll call it R because your book is calling it R. But most of the time, R is written as rho, right? So we're going to call this, you know, if I call it R, well, I can call it small r, and then that would not interfere with me calling the spherical coordinate systems capital R. So, okay, you know, I'd rather call it rho. I'm going to call it rho. Most of the time you see it as rho rather than r, or small r, or a large r. So just think that in your book, when I'm writing rho, your book actually writes it as r, but you see the idea. So what we've got is we've got rho, z, and phi. Oh, you know, on this, by the way, on all three of these, I thought I'd mention this, is that I hat is the unit vector in the x direction, right? J hat is the unit vector in the y direction, and k hat is the unit vector in the z direction. So let's keep those in mind, because I'm going to talk about the unit vectors in all three of the orthogonal directions here too. And I think everybody can see that we've got, you know, like that would be a 90-degree angle right there between rho and z. And then phi, what is phi? Phi, I'm going to draw this in the xy plane. Phi is the angle. I put a little bit too much ink there. There we go. There we go. Okay. So phi, or yeah, is the angle between the positive x-axis, or where the positive x-axis would be. So we really can't use cylindrical coordinates without using some type of reference to Cartesian coordinates, can we? Spherical coordinates are the same way, by the way. So this is the angle. So if I wanted to denote a point, a singular individual point in space, it would have all three of those variables. Okay? Now, how do these extend? Well, if we look at them just like we looked at the characteristics of the x, y, and z axis, I think everybody can see that the rho extends from 0 to infinity, right? This can go all the way down to 0. It can be a distance from the origin all the way down to 0, or it can go all the way up to infinity. It can't go to negative values, though, can it? No, it can't go to negative values. We don't need negative values for rho to define any point in 3 space using rho, z, and phi, right? So I just wanted to point that out. How about z? Well, z is the same as it was. It goes from minus infinity all the way up to plus infinity, just like it did with the Cartesian coordinate system. And you might say that in some way this is sort of a hybrid. You know, it's using the x and the z and the y and everything else. And we can figure out our conversions in just a second. I'll do that in just a second. But let's look at the last one now. Let's look at phi. What does phi go from, and what does it go to? Well, it starts, if it was all the way along, if phi was right along, or r was, you know, right along, the point we're discussing was right along. Did I say right along enough? Right along the x-axis, right? Then it would be 0. Phi would be 0. And then phi can extend all the way around that xy axis, so it can go from 0 all the way up to 2 pi, right? So these are our borders, or our constraints. Just like we had an unbounded set of constraints on our x, y, and z orthogonal axes, we now see that we only have the z that's going from minus infinity to positive infinity. Rho has been cut in half. It goes from 0 to infinity. And phi only goes from 0 to 2 pi, right? But with these three orthogonal, and aren't they orthogonal? You know, phi goes in this direction, r goes in this direction, z goes in that direction. So all three of those are orthogonal to each other. Rho is perpendicular to z is perpendicular to phi, right? Same here. You know, x is perpendicular to y is perpendicular to z, isn't it? So we have three orthogonal or, 90 degrees perpendicular axes. Here we have three 90-degree independent axes, okay? Now, let's look at a couple of things here. What if I was to hold z constant, right? Just like we did in the Cartesian coordinate system. What if I was to hold z constant and I was to let x and y vary? Well, I would get a plane. Did I say x and y? I meant rho and phi. What if I was to let rho and phi be any value they want to be? I would get a plane, wouldn't I? Where have I seen that before? There we go, right there. How about if I was to hold rho as a constant? What would I get then? Right? So rho is a constant. It's right here. I could let z change, right? I could let phi change. So what I would get is a cylinder. Does everyone see that? What if I held phi constant? Right, so phi, let's say that we're holding phi right along here. It's constant. I let r change to anything it wants to. I let z change to anything it wants to. So again, I get a plane, right? When we look at the unit vectors in each of those three directions, the unit vector in the z direction, of course, is just going to be k. The unit vector in the rho direction is just going to be rho hat. And the unit vector in the phi direction is just going to be phi hat, right? One unit in that direction, one unit in that direction, one unit in that direction. And so those are our three unit vectors. You know what else I would like to do is to look at a differentially small thing on cylindrical thing. Just a second. Well, let's look at a differentially small volume. Now, we've looked at that in the last, lecture, and for the Cartesian coordinate system, and using that type of thing, that would be dz, this would be dx, and this would be dy. And a differential volume then is going to be dx, dy, dz, and everybody can see that. Now, with the cylindrical coordinate systems, it doesn't work quite that way. A differential element that we see, let's say that this is my z-axis, right? That's my z-axis. And so if I was looking at a differential element, let's just draw a differential element. I'm just going to draw the top here first, right? Those are two r's. and that's out from the z-axis. And let me see if I can draw this well. That's the top of it. That is not too bad, is it? Okay, so this distance right here is going to be dr, isn't it? Everybody see that, right? And you know, this distance right here, right, is going to be, I'll just draw a thing. That distance right there from here to here is going to be r d theta, right? Because this right here, oh, I better follow that back there. This right here, that is d theta, isn't it? Right? And theta goes around in that direction, just like I've got it up here, right? Here's your, or did I say theta? I meant phi. Oh, I even wrote theta, didn't I? No, that's phi. And that is phi. Sorry. Yeah, I switched back to theta for some reason. I don't know why. So I've got d phi here, and let's just look at a regular two-dimensional arc, right? If I have a two-dimensional arc like that, what is the distance of the arc if I know that I've got that arc is subtended by a radius through that angle? I'll put theta there, why not? And that's right. S equals R times theta, doesn't it? And that's the same thing that we've got here. So this length right here is is dr. This length right here is r d theta, right? Because that's d theta, and the distance out to there, right, is r. So that's r d theta on that side. So if I wanted to look at, now you're probably saying, well, what's this side? Well, that would be dz, wouldn't it? So if I just wanted to look at this top surface of my differential element, just the top surface. So the area of the, you know, why don't I call it S of the top is going to be R dr d phi. I hope no one has any questions about that. And what I should put here is ds, because that's a differentially small surface area on the top, right? So let's do that. So ds of the top is r dr d phi. Now let's look at the surface area of this side here, right? That front side. Well, I think everybody can see that this distance right here is going to be r d phi, or I could say r plus dr d phi. We could write it that way. Well, so this length here we could really say is r plus dr times d phi. But the truth is we don't, because r plus dr is so small that dr times d phi is such a small number. It's an infinitesimally small number that we don't have to really worry about that. So r plus dr really approximately equals r d theta. So that's what we're going to write. So if I look at that front area, so d sub s of the front is going to be r dr times dz. So r dr d. Did I say dr? That's r d phi. There we go. R d phi dz. Hold on. So that's the front. R d phi, that should be a phi. dz. And then what if we want the side over here, right? So ds of the side, well, we know that one side is going to be dz, and we know the other side is going to be dr. So dr dz. This side is dr, this side is dz. That makes that dr dz. And so there you go. We've taken care of the cylindrical coordinate systems. I just want to see if I want to say anything else about those. We've got, oh, that's right. We haven't got the differential volume, have we? So the differential volume, where can I put that? I'll put it right here. D volume. Well, it's going to be dz times dr times r d phi, right? So let's start off with r. So it's r d phi, but we got a dr in there. So r dr d phi dz. That would be the incrementally small differential volume that we have for cylindrical coordinates. Of course, that's what we wanted to do. And now spherical coordinates, I think I'm going to actually, I don't really have the room, nor do I think I have the time. I should have an automatic timer that goes on that just lets me know. Well, with spherical coordinates, it's not like Cartesian or, well, in some ways, spherical is similar or shares some characteristics with cylindrical coordinates. All right, now let's look. I'm going to overlay this just like I did before on our Cartesian coordinate system. So if I've got a Cartesian coordinate system, I'll draw it the same way that I did the last time. This is your x, this is your y, this is your z. Now, when we look at the three different coordinates, three orthogonal coordinates that you've got here, you've got, let's say, a radius r. I'm going to pick a point in space. So that's going to be capital R. That's what your book uses. Usually it's a smaller. I'm going to drop this down so that I can make a projection of that length vector or whatever it is on the XY plane. So that's R. And this here, if you wanted to look at that right there as theta, right? So rotated off the XY axis is theta, right? So theta is the angle that R is rotated off the XY axis. And in fact, you could say that, hey, isn't that a right triangle there? Doesn't that make a right triangle? And if it does make a right triangle, then couldn't I say that this is really the projection of R into the XY plane? So why didn't I call that R cosine theta? Right there. I think everyone can see that. Now, if I wanted to find out what the rotation of R cosine theta is off the x-axis, that would be this angle, wouldn't it? And we know what that angle is. We remember it from cylindrical coordinates. That angle is phi. So I have R, that's the length of this thing. If I was defining this thing in 3 space right here, I could define it with R, phi, and theta. So those are the three coordinate systems that we've got here: r, phi, theta. And what are the characteristics of each of those? Well, first of all, r is the distance from the origin out to where that point is. So if we looked at what the boundaries on r is, r would be greater than 0, but r would be less than infinity. How about phi? You know, phi here, since it's occurring in the xy plane, is the same as the phi here, isn't it? So if we go back to the phi, we see it's 0, between 0 and 2 pi. So 0 phi 2 pi, right? Because that goes all the way around. So phi would go all the way around here, and that's got to be 360 degrees, and that's where the 2 pi comes in. All of that line, by the way, is laying in the xy plane. Okay, how about theta? Well, theta doesn't have to go to 2 pi, does it? Theta only has to go, if I was to extend, you know this line here, if I was to extend that out onto the other side, right? Theta could just go from here all the way over to there. It doesn't have to go under. It would just be redundant if it went all the way under. So all theta does is theta just goes from here to here. So theta only goes from 0 to 180 degrees, 0 to pi. And so that is our spherical coordinate system. Now, if I wanted to hold one of these, let's say that I wanted to hold r, what would that be? So if r equals a constant, and I let phi and theta change, that would be a sphere, right? Does everyone see that? If I hold r constant, I let phi go all the way around here, right, to 2 pi. I let this go all the way from that to 2 pi. What it would form is a sphere. What if I held phi constant? If I held phi constant, but I let r change from whatever, and I let theta change from whatever, I'm going to end up getting a plane, right? And what if I hold theta constant? What would that give me? If I held theta constant, I would also, no, I would get a cone. What am I thinking? Okay, so let's hold theta. So theta constant, that always there. And then I let r be as far as I want to. In fact, it would be a cone that could go out to infinity, couldn't it? Because I'm holding theta constant. I'm allowing that to go all the way around there, right? So wouldn't that create a cone? I'll put constant down here so that you can see that it's constant. That's what it would create if it was held constant. All right, like I said, I forgot to put my timer on, and it's not a good thing, but usually one sheet of paper is about 35, 40 minutes, so we'll see how this worked out. I also might try and even dial this in. The focus, you know, it almost seems like it's still trying to do that. But I was told that it comes back much better now that I've taken the autofocus off. And there still seems to be like some autofocus stuff going on here, but it's not as bad from what they tell me, although it looks like it's just as bad. I'll try and work with it and see what I can do. Okay, thanks a lot.